students, welcome to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today, our topic is the mathematical modeling of mechanical systems. These are the contents. We'll discuss in this lecture is translational and rotational systems, how to draw the free body diagram, the parameters of the mechanical systems, the mathematical model of mechanical systems, and mathematical models of liquid level systems. So, consider the translational systems. Actually, the mathematical model consists of a collection of equations describing the behavior of the system. The dynamic behavior of the system is represented by the set of differential equations which are obtained based on the fundamental laws of the physical system. In the last class, we have studied that for electrical systems, we have applied the KCL and KVL. And here, we will apply the Newton's law for the mechanical systems. The mechanical systems can generally be classified as the translational systems and the rotational systems. The translational system is related to the force and the translational motions, whereas the rotational system is related to torque and the angular motion. Next is the fundamental components of the translational system. The first one, it is considered as a mass, and mass is a mechanical element and it has some inertia. And when a force F is applied to the mass, then the displacement takes place. Suppose in this direction is given, x1 is the direction of the displacement, and due to this, an opposite force F of m is generated in the opposite direction, and that is known as the reaction force. And the reaction force F of m is proportional to the acceleration, or we can say this reaction force is equal to mass into acceleration. A represents the acceleration and A is equal to b square h dt square, where h is the displacement of the system. So, using the Newton's law, we can say the total force applied capital F is equal to md square x to dt square. And we have considered that the mass is concentrated at the body. The next is the spring. The spring stores energy during the variation of its shape due to the elastic deformation resulting from the application of force capital F, and due to the application force capital F, a restoring force F of k is produced, and this force depends on the stiffness constant small k and the displacement. So, Fk is the k into small x, and according to the Newton's law, total force applied force F is equal to k into x for the 1/6 spring. And when we consider the spring whose both ends have the displacement x1 and x2, so for that spring the total force F is equal to k into x1 minus x2. That means we have to consider both the displacements. Next is the damper. The damper is one-ended fixed over here, and for this damper both the displacements are connected. And when a force F is applied to this dash spot, then a reactive force F of B is produced, and which is proportional to the velocity. So, Fb is written as d into dx dt, where d is the force plus friction coefficient and dx dt is the velocity, if we consider x as the displacement. So, for the one end fixed dash spot, the equation is total force equal to b into dx dt, and for both displacement we have to consider the displacement b into dx1 dt minus dx2 dt. So, these are the fundamental components of the translational system. Next is the rotational system. The rotational system is related to the torque and the angular displacement. Here the torque is represented by capital T and the angular displacement is represented by the theta. Now, the first is the moment of inertia of mass, and we have assumed that it is concentrated at the center of gravity of the body. Now, due to the application of this torque, capital T, it produces an angular acceleration, and the reaction torque Tj is equal to J into d square theta dt square, where theta is the angular displacement and d square theta dt square is the actually angular acceleration. So from Newton's law, we can say T is equal to the Tj equal to J d square theta dt square, and J is the moment of inertia. Next is the spring. Now, due to application of the torque in the spring, it is twisted by the angle theta, and the spring will produce an opposite torque that is equal to Tk. For the 1 inch stick, this Tk is equal to k theta. So the total torque applied T equal to k theta, and when both ends are free, then capital T, that is the total applied torque, equal to k into theta 1 minus theta 2. That means both the displacement have to be considered here. Next is the dashpot or the damper. Now the dashpot, when torque is applied to the dashpot, and then it is opposed by the damping torque, that is Tb, and Tb is equal to b into d theta dt, where b is the viscous friction coefficient and d theta dt is the angular velocity. If both ends of the dashpot is not fixed and both ends have two different theta 1 and theta 2, then we have to consider T is equal to b into d theta 1 dt minus d theta 2 dt. Next is procedure of drawing of free body diagram. Now, to draw the free body diagram, first we have to consider some assumptions. So, first is the direction of the displacement, that means the direction of the force, or for the rotational system, the direction of torque or the mass as the positive direction. Then we have to find out all the forces for translational system and all the torque for the rotational system. Next, we have to apply the Newton's law of the motion. So let us consider the example 1. In example 1, a mass is connected with the spring and a dashpot, and the force is applied to the right hand side direction, and due to this direction of force, the displacement occurs, that is xt. Now we have to consider the free body diagram of mass m. Before drawing the free body diagram, we have to consider one more point, that is the inertia force will always opposite of the acceleration, and the acceleration and the displacement have the same direction. And if we consider the spring and the damper, then for the extended spring, so after application of ST, the spring is extended, then force is working outward of the body, and if that is compressed, then it will act towards the body. So this is the mass m, force is connected in this direction and displacement is this direction. So acceleration have the direction same as this displacement, and the inertia force Fm will have the opposite direction of this displacement. So Fm is acting in this direction. Next, when we apply the force in this direction and xt is in this direction, that means the k and b both are extended. When a and b both are extended, then they will exert the force on the direction outwards the body. Hence, the opposite direction force is equal to summation of all these three forces. So we can write the capital F is equal to md square x dt square, that is the Fm, plus d dx dt, that is the Fb, plus kx, that is the Fk. Next, consider the second example. Here the moment of inertia is given and torque is applied. Due to that torque, the theta is rotating in this direction. In the same manner, for this moment of inertia, the torque due to this moment of inertia, the force torque due to the viscous coefficient and the spring will act on the opposite direction, and the summation of these three torque is equal to the total applied torque. So total P is equal to Z square theta dt square plus d theta dt plus k theta. This is the P of J. This d theta dt is the TD and k theta is the K into K. So these are the parameters of the mechanical system. So these are the parameters of translational systems, the quantity and the symbol and the units are given. And here for the rotational system. For an example, we can say in the translational system, we'll use the force. The symbol of force is Ft and unit is Newton. Whereas in the rotational system, we'll use the torque and which symbol is capital T and unit is Newton meter. So these are the different parameters that are used in both translational and rotational systems. Next is the mathematical model of mechanical system. Here we have to describe the mathematical model of the given system. Here two masses M1 and M2 are connected. This one end is the fixed end and B1, B2 and K1 and K2 is connected in between M2 and the mass 1. The total force is applied in the downward direction and due to the application of force, the mass 1 has displacement of x1 and mass 2 has the displacement of x2. So we have to write the differential equations for this model. So first we need to draw the free body diagram of mass 1. So first consider the mass 1. When mass 1 is considered, the applied force is in this direction, downward direction. So the displacement is given as the downward direction. So the inertia force will act on the opposite direction of this displacement. So Fm is the opposite of the displacement. Similarly, when M1 goes downward, that means the B1 and K1 both are extended and this B1 and K1, due to this B1 and K1, the force of K1 and B1 will act outwards the body. So the summation of all these three forces is equal to the opposite force F of T according to the D'Alembert principle. So F of T is equal to M1, the mass 1, d square x1 dt square plus now B1. Now B1 is connected in between mass and mass 2. So we have to consider both the displacement. So B1 into dx1 dt minus dx2 dt plus K1. Again the K1 is connected between M1 and M2. So we are considering both displacements. So this is the first equation of mathematical model. Next we have to consider the mass 2. Now mass 2 is connected with both B1 B2 and K1 B2. So when mass 2 goes to the direction of the displacement, B2 and K2 both are extended, and for the extended string, the F of K2 and F of B2 will be in the outward direction, because for the extended spring or extended damper, the force working is outward the body. And due to this displacement, this direction, the inertia force will act in the opposite direction of this displacement. So F of M1 is acting in the above direction. Now for the damper and the K1. So when M2 goes downward direction, and it is also going to downward direction because this end is only fixed. So B1 and K1 both are in the extended position. So F of K1 and F of B1 go in the downward direction. So using these two, we can write the total force F of K1 plus F of B1 is equal to the force F of K2 plus F of M2 plus F of B2. Now what is F of K1? Now K1 is connected in between the mass 1 and mass 2 and both displacements are working on it. So K1 into x2 minus x1 plus same is applicable for B, that is B1 into dx2 minus dx1 dt, that is equal to K2. K2 is connected only for M2, so K2 into x2 plus B2 is only connected to M2, so B2 into dx2 dt plus due to this force M of 2 d square x2 dt square. So these equations 1 and equation 2, these two are the mathematical model of the given mechanical system. Next is the mathematical model of the liquid level system. So consider a liquid level system over here, and through this tap the fluid is flowing through the tank, and one valve is connected to this, and Qi is the volume inflow rate of the system. Now, due to this output channel, one valve is connected also in the output channel, and R is the resistance of this outflow, and Q0 is the volume outflow rate. So here we will assume that the liquid is incompressible. Basically, the fluid can be divided into two categories. One is incompressible and another is compressible fluid. Now, if the density of the fluid remains constant despite the change in pressure, then the fluid is known as the incompressible. Otherwise, it is compressible. So, in practically, most of the fluids are compressible to some extent. But here, we will assume that the liquid is incompressible. Next, A is the area of the cross-sectional area of the tank, and small h is the level height of the liquid. And for this liquid, we will consider rho is the density. Now we can obtain that mass of the tank will be rho into A into H. Now what is the rate of change of mass? The rate of change of mass is the m dot, and that is equal to rho, that is the density, into the total mass inflow rate minus the total outflow rate, where Qi and Q0 are the volume inflow rate and volume outflow rate. So from this equation, mass of tank equal to rho A H, we can write down that m dot, that is equal to rho into A into dH dt, where A into dH dt is equal to Qi minus Q0. Now the Q0 can be written as the ratio of height of the liquid level H divided by the resistance to flow through the outflow valve. And rearranging these equations, we can write down Ra into dH dt is equal to R into Qi minus H, where Ra is the hydraulic capacitance of the system, and this equation represents this Ra into dH dt equal to Ri into Qi minus H represents the mathematical model of this given system. So in this class, we have learned about the different mathematical modelings of translational system and rotational systems, the different parameters, and the mathematical models of liquid level systems. And these are my references. These two are, they can be textbooks, K. Ogata and Anand Ratarajan. And thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.